All right, chapter 3-2, we're going to be talking about the rational number system. And the first thing I want you to do in your notes is I want you to draw this graphic, okay? The big square all around the whole thing is your whole rational number system. And then the circles inside of it get smaller and smaller. So take a minute to draw that. And we'll do examples and say what everything stands for here. All right, so we're going to talk about what each term means, okay? So, and actually, I think I'm going to start in the middle this time and work our way out. So, in the middle, we have that N, and that N stands for natural numbers. It's called natural. And if I was to ask somebody, Colton, if I was just to say, start counting, what would you do? Go ahead, start counting. Where'd you start? 1. That's your natural place to start. So natural numbers start at 1 and they go up for eternity, but it's always just whole numbers, just how you would naturally count. If I said count, you'd say 1, 2, 3, 4, 5, 6, 7, 8, forever and ever, right? Those are your natural numbers, just how you naturally count. The W stands for whole. It's a silly memory trick, but whole just adds a donut hole. Whole numbers just add the 0 to the naturals. So instead of starting at 1, you add the whole, the 0. So now you're 0, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 forever and ever. Okay. Now the Z is kind of strange to me. I don't know why. So I took this graphic from the textbook, and your worksheets are also from the same, it's a matching workbook that goes with your textbooks. However, in the textbooks, it has a Z, and in your workbook, homework, it calls it an I. So I want you to put Z or I, because I want you to know that either one you see means the same thing. And it stands for integers. Does anybody know what, we've talked about it before, but does anybody know what integers adds in to the naturals and the wholes? Yes. Yeah. Integers just goes both ways on the number line. It's still your whole numbers. So integers is negatives all the way back for forever. I'll just start at -2, -2, -1, 0, 1, 2, forever this way, forever backwards. So your integers adds in your negatives, okay? And then the last one, that's that outside Q, okay? This Q stands for rational numbers. Or just rational. You don't have to put the word numbers. These are all numbers. I'm not going to put numbers. Rational. Now, rational, of course, is going to include integers, wholes, naturals, right? But it's also going to include, notice each time we've gotten a little bit bigger circle, we've added something, right? So we started out with just 1 to infinity. Then we added a 0. Then we added negatives. Now, when we get out to rationals, we're adding fractions, okay? So if you want to put right here under rational, it's fractions, and it's both negatives and positives. So rationals adds or includes fractions. And then we talked yesterday on our homework about converting fractions to decimals, right? And today we're going to do decimals to fractions. So under fractions, this is going to include some decimals. So I want you to write this out here. Whoops. Fractions includes some decimals, and we'll talk about which ones are included and which ones are not. So all fractions are included, but if it's in decimal form, not all decimals can be written as a fraction. So that's why all fractions are included in rationals, but not all decimals, just some. And here's why. Some decimals, like the first kind, are the kind that stop. Decimals that just stop. Examples of that would be 0.4, right? It just stops. Another example of that would be negative 1.256. It just stops, okay? The other kind of decimal that's included are the kind that are repeating. So repeating decimals are considered rational. And an example of a repeating decimal would be 0.6 repeating. Or another example could be negative 2.81 repeating. Okay. And the reason is because these two, I always say they make sense. Okay. They either stop, they have a finite end, or at least repeating ones have a pattern, right? 81, 81, 81, 81, they make sense. What is not included, and I want to have you make a note of this, not included, so not rational. Those are called irrational, okay? So go ahead and write not in the rational column are irrational numbers, and I'm going to give you some examples of irrational numbers. I think every family has a crazy aunt, right? Family reunion or get together, they just go on and on and on and on, and they never stop talking, and they don't make any sense, and you think they're crazy, right? They're irrational. Irrational numbers go on and on and on with no pattern. They don't stop, they don't repeat, they just never end, okay? So think of your crazy aunt when you're trying to think of irrational numbers, right? Does anybody know kind of the most popular example of a number that goes on and on and on? Yes. Pi. Yeah. Pi is an example of an irrational number. Okay. 3.141529. That's all I got. Goes on forever. I don't remember it past that. Another example, and it's not something we will mess with in this class. You won't even mess with it in algebra. It's not until you get into maybe algebra 2, but it's called E. You don't need to know what it is, but for Khan Academy, you do need to know that it's irrational. It's not going to show up on your worksheets, but it will show up in Khan Academy. So when you're trying to decide if something is rational or irrational, if it has pi anywhere in it, or if it has E anywhere in it, it's considered irrational, okay? Another example of an irrational number is the square root of anything not perfect. So I'm just going to put an example here of like 20. So does anybody know what your perfect squares are? 1, yeah. Yeah, if you want to. Just go up to, say, 100, if you can. High as you can. Okay. Is what? Yeah. So if you take 1 times 1, it's 1. 2 times 2 is 4. 3 times 3, 9. So 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. That just takes you up to 100. Those are considered perfect squares. Perfect squares go over in the rational column. Why would a perfect square, like let's say you just said 81. Why would the perfect square, or why would the square root of 81 show up on the rational side? Well, it equals what? Yeah, it equals a whole number. So the square root of 81 could actually be technically a natural number because it equals 9. So it's all the way up in the naturals. But the square root of a non-perfect number like 20, or the square root of 5, or the square root of anything other than those perfect squares is considered irrational. Because if you punch it in your calculator, there will be no end and there will be no pattern. Okay, and you can't write it as a fraction. Okay, are we good there? All right, so I want to talk about classifying numbers within our rational system here. So we've got some examples here. So what about the number 0.87? We're going to do these examples right here. I want to classify 0.87, and I want to name as many as possible that it fits into. Okay, so if you start in the naturals, does 0.87, is it going to be natural or whole or an integer? It's not going to be any of those because it's a decimal, but it's a decimal that stops, which means it fits where? Colton, where does it fit? 0.87. It's not natural, so it can't start in there. It's not whole. It's not an integer, but it's a decimal that stops. So where does it land? Yeah, and you just put a Q, right? It lands in the rational. Okay, it's not natural, it's not whole, it's not an integer, but it is a rational number. Okay. How about negative 23? Is negative 23 a natural number? Sophia, what do you think? Negative 23, would it be natural? No. Would it be whole? Whole is 0 and up. Nope. Would it be an integer? Okay, so it starts in the integers, and you can put I for integer. That's what your homework tells you to put. If it's an integer, it's automatically a what? A rational. It always blows out. Whatever it is, it's at its smallest part, it's everything else out. So list them both. It's an I and a Q. Now, we said that rationals have to be fractions, but we're saying that negative 23 is a rational. Why is that a fraction? Blake? Yeah, every whole number is a fraction. We just, mathematicians are lazy, right? We don't ever put those numbers in there. Every whole number can be written as a fraction by just sticking it over a 1. So technically it is a fraction. Okay. How about 2/3? Automatically, because it's a fraction, it automatically is not natural. It's not whole. It's not integers. It's a rational. Good. How about negative 2.56 repeating? Damien, what do you think? What is it? Yeah, because it's repeating, right? It makes sense. It has a pattern. It is just rational. Obviously, the decimal makes it not any of the other ones. Let's see. Braylon, how about 1.5? It has a fraction, so it's automatically not natural, whole, or integer. But would it be rational? Does it have a fraction? Then it's rational. Okay, how about the number 4? Inlo, what do you think about the number 4? Where would I start? Huh? I'm looking here. Whoops, I just erased it. I'm looking at this. I'm doing examples here, and I'm wanting to see where does this number 4 fit in our rational number system? What's the smallest one it fits on? Huh? Okay, it's natural, which means I blow out to what? It's natural, it's, keep going. You skipped one. It's natural, it's whole, it's integers, and that makes it part of rational. Good. Start at the smallest part it fits and blow out and include everything else. Okay. How about pi? Does pi fit in our rational? Yes. Yeah. Pi is irrational. Okay. So pi does not fit at all in our rational number system. And then last but not least, the number 0. Where would be the smallest we could start with putting 0 in? Sophia? Good. Sophia would go in whole numbers. No, 0, good job, Sophia, would go in wholes. And then what else does that mean? It's wholes, which means it's integers, which means it's rational. Good. All right, are we good there? Because you're going to have to, on your homework, you're going to have to identify whether or not something, where something fits. And I think in your homework, It doesn't even include naturals. It just says whole, integers, and rationals. Just know that if it's whole, it's automatically integers and rationals, right? It automatically blows out. All right, so now we're going to go up and do a couple of examples of writing each number as a fraction. So if we want to write the number 29 as a fraction, Blake's already said it. All we have to do is put it over 1. There we go. We just wrote 29 as a fraction. It even works for 0. Put it over 1. Okay. Any whole number, which means we're really any integer, because negatives and positives, it works. Any integer can be put over a 1 and turned into a fraction. Doesn't matter if it's negative. If it's negative 47, you just write negative 47 over 1. Okay. What about mixed numbers, mixed fractions? If we want to turn this into just a regular fraction, actually it'd be an improper fraction, but what do? Blake? Yeah, you multiply these, and then what do you do with yep, you add 7, and then you use your same denominator. So 8 times 3 is 24. 8 times 3 is 24, plus 7 equals 31 over, keep your denominator. And that's your final answer. You reduce if you can, but on these you shouldn't be able to reduce. You won't be able to reduce mixed ones. Multiply and add, keep your denominator. Okay. So it doesn't matter if it's a negative, right? Same thing, multiply, then add. So 5 times 7 is 35. Add the 6, gets you 41, keep the denominator, but then don't forget, if the whole thing was a negative to begin with, your answer has to be a negative when you get done, okay? So you kind of ignore the negative while you're doing your multiplying and adding, then you add it back into your answer. I think that that's good on that. I don't think we need to spend a whole lot of time there. All right, so now I want to spend some time here on writing decimals as fractions, okay? Regular decimals that stop are not a problem, okay? They're pretty simple. Know that when you're dealing in the decimal side, so this right here is considered the 10th spot, and this right here, the 2, is considered the 100th, okay? So if we want to write 0.32 as a fraction, we put 32 on top, and then underneath, since this goes all the way out to the 100th, we put a 100. Okay. You don't even need to know the name of all your spots, 10th, 100th, 1000th, all. You don't need to know it. All you need to know is that there are 2 decimal spots after the decimal, so you need 2 zeros in the bottom. Yes. Yes. Yep. We're getting to that. So when you're writing your initial fraction, you take your number that's here, right? 32. You write it on top. 32 is 2 decimal places, so you need 2 zeros underneath, so it's 100. Now, okay, like Colton said, you got to reduce if possible. Always reduce if possible. If you're not sure what it's divisible by, they're both even. You can always start with 2. If it happens to pop out at you that they're also divisible by 4. Yes. Oh, were you going to say 4? Oh, what's the answer? Yeah, so if you wanted to start with 2s, you could do 16 over 50, but those are both still even, so you would need to keep going, and you would get to 4 over 25. 4 and 25 don't have any common factors, so that means that is as reduced as it can be. So 4 over 25 is your final answer. Okay? No, 8 over 25, not 4. Sorry, I don't know where I got that. There we go. They're both divisible by 2, which would be 8 over 25. Yes.
Last year, our math teacher, we had like a big thing about putting the power. So you want to like divided by 4, 532, and 100.
No, you don't have to. I mean, if it helps you, to know why you're doing it, but I think when you're learning the concept, writing out the steps can help. But that should be, I think you guys are okay on that. So if it helps you, you can do it, but you don't have to. What he's saying is if you know they're both divisible by 4, if you want to put divided by 4 and divided by 4, and you know that's how you get 8/25, you can do that if you want. Okay. If that helps you to know, if that helps you reduce them, it's not going to bother me a bit, but you don't have to. Okay. So what about one that has a whole number out front? It doesn't change anything. Okay. Your whole number stays your whole number. And then your decimal, this part right here, okay, becomes your part of a mixed fraction. So 75 over 100 because of 1. And then because it's 2 places, it's 2 zeros. And then the last thing you would do, the whole number is going to stay your whole number, but you could reduce 75 over 100 to what? Does anybody know? Yeah, 3/4. They're both divisible by 25. And your original was not negative, so you don't have to worry about adding a negative back in. So that would be your final answer. Now I want to talk about one. This is the only hard part of this whole section, and I want to show you how to do it, okay? Converting repeating decimals to a fraction is a little bit more work, okay? So I'm going to show you the steps. As long as you follow these same steps every time, it's not hard to do. It's just, you got to follow the steps. So I'm going to rewrite my repeating decimal as point. I'm just going to go 4 out. It doesn't matter how many you go because it's repeating. So really it goes forever. And I'm going to call that my number. So I'm going to name it n. Okay. I'm just naming it n because it's my number. Now in math, as long as you do the same thing to both sides of the equation, it doesn't matter what you do. Everybody agree with that? So if I multiply this side by 10 and I multiply this side by 10, I have not broken any math rules, right? And I would reduce that, and that would be 10n over here. And when I multiply 0.8888 by 10, multiplying by 10 just means you move the decimal 1 spot over. So when I rewrite that, I'm going to write that as 8.8888. .8888. And again, it doesn't matter how many 8s you put because it goes on forever and ever. Okay. So I've multiplied both sides by 10. In doing that, I've rewritten my repeating decimal now as a 8.888888. So I move my decimal over 1. Now I'm going to write my original problem, which was n equals. I'm going to write it right underneath here. So n equals, I'm going to keep my decimals lined up, 0.8888. Right? I'm just writing it right underneath my manipulated one. And then I'm going to draw a line. And I'm going to subtract these 2 lines from each other. So 10n minus, and really what's there in front of that n that's not there? A 1, right? So 10n minus 1n is how many n's? Minus 1n, 9n. And if I subtract these 2 right here, what happens? This to infinity cancels each other out. And all I'm left with to drop down is the 8, because the 8 had a 0 there. And so the 8 didn't lose anything in that subtraction problem. Now we just have to solve for n. Divide by 9 and divide by 9. And you get your new number, or your fraction is 8 over 9. It can't be reduced. So I'm going to go back up here. I'm going to write that this equals 8 over 9. And that is your fraction that is a repeating decimal. Okay, and we'll go through this one more time. Yes. The reason I multiply both sides by 10 is because I need to move that decimal point over 1 so that when I subtract everything, all my decimals disappear. Yep. And we'll do one more example really quick. And then I know we're running close on time. So let's do one more example. I want to do this one right here. Now, I'm going to do something right now so I don't forget it. For my answer, I'm going to put a negative sign because my answer is going to be negative, but I'm not going to mess with the negative in this whole nth thing, okay? So I'm just going to put the negative there so I don't forget it. All right, so I've got my n equals 6 point, and then go out however many you want, 2 or 3, it doesn't matter, 3 or 4, it doesn't matter. Okay. Now I'm going to multiply both sides by 10, right? Multiply both sides by 10. And when I do that, I get 10n equals, now keep in mind, multiplying by 10 just moves this over once. So my new number is 63.333. Okay, it doesn't matter how many threes you write afterwards because they're going to go away anyway. Now I'm going to rewrite my n equation again. I'm going to keep my decimals lined up. My original one was 6.33. Oops, wait a minute. Yeah, that's right. 333. Sorry, confused myself there for a second. Draw your line. Everything from the decimal point on, right? Everything from here back cancels each other out. That's why it's important to line your decimals up when you write your 10 in and your n. And what am I left with? I'm left with 9n equals 63 minus 6 is 57. I'm going to divide by 9 and divide by 9. And I get n equals 57 over 9. And in the instructions, it says write your answer as a mixed. So we need to turn this back into a mixed. So how many times does 9 go into 57? Yes. 6, which is 54, which is 3 left over. So 3 over 9. And then I would reduce that 3 over 9 to 1/3. Now I'm going to go back up to where I'm going to write my actual answer. That's where I stuck my negative sign. And I'm going to write my answer as 6 1/3. But I know it's negative because my original problem was negative. The nth ones are the only ones I think that are really going to give you any challenge. And if you just follow these steps every time, I think you'll be okay. All right. Let me get you your paper before you leave me. For those of you at home, click load on Cami, make sure you show your work and email me if you have any questions.